Okay, let's start our class. Uh, Welcome back to this introduction to Edge AI Technique 1 class. So first of all, just to let you know, we have finished the basic concept and the Python tutorial. So from today's class, we'll formally start machine learning. Although we mentioned we have finished the Python tutorial, there are many topic related functions or codes we will introduce, gradually in this class. The lecture two Python tutorial, this covers, most those most commonly used those codes or syntaxes or structures. It's actually not only for this specific course, but also for it's actually for the general Python programming, not just merely for the machine learning class. Okay, so now we can go to lecture three, open linear regression one. By the way, for lecture four, I'm not sure today how much will we cover about lecture four, or can we cover lecture four? But in the next class, please re-download this one because I realized that I realized I forgot to add the 3D training, 3D plotting, sorry. Here I just, showed the techniques for 2D. So extend the 3D here in lecture four. Let's start. Actually, I can open right here. Let's start our linear regression one, lecture three first. Okay. So first of all is the motivation of a linear regression. So for example, if you have seen the data like this way, so we can say that it somewhat, it has somewhat like a linear trend. So the point is that I want to use a function, let's say here a linear function to tell the trend. So what's the point for me to tell the trend? Imagine, for example, those points are stock, no, stock data. So if I can tell the trend, I can make a prediction for future data, right? So that suppose my prediction is correct, I can earn a lot of money in stock market. So this is the motivation for the prediction. uh One thing I do want to mention here is that I write it as a y response, x attributes, not attribute, it's attributes. It's t dimensioned. The meaning here is due to the limit of our plotting, we can only plot 2D, 1D, 2D, or 3D, things. No one can plot 4D, I'm afraid. Otherwise, you can easily get a Nobel Prize. However, in the real cases, if you just have like a one attribute versus one response, it's practically it's super simple, and typically it won't be the case. In a typical, in a practical example, you might have hundreds, thousands, even millions of attributes versus one response. The response could be do or not to do, which is actually a classification problem. Or let's say again, go back to the financial data. Let's say suppose I have, whatever, I'm not sure whether you guys are a fan of Bitcoin. Let's say finance.google.com, and I can say Bitcoin's here. Okay, so we can see for example, year to date, the trend is something like this way. So you can see this is the price, and this x-axis is the date or 5 year, whatever. Oh, great! If you put a $1 here, how much can you earn now? Probably more than actually, I don't know, more than $10, $11 maybe. So it's about 11 times, right? Okay, so clearly in this example, a Bitcoin example, our y-axis is the price. I'm interested in, say, today is May 29th, 2025. I want to ask, hey, what will the close price for Bitcoin be for tomorrow? Let's say at the same time now, at 5:05. I'm in CST zone. So 5:05 CST tomorrow. What is the time? What is the Bitcoin's price? So this is my response, which is which is 1D, one dimensional, which is, however, your x-axis, of course, in this, in this price chart, of course, the x-axis is just a date. It's super simple. But when you want to make a prediction for tomorrow's price, you probably cannot only cannot only consider the time and date, which is too simple, right? You can consider many different things. For example, the candle. I cannot show the candle chart here. I'm not sure if I have Yahoo. If I go to finance.yahoo.com, then I go to, let's say, Bitcoin, Bitcoin's here. Oh, okay. Now if I click chart, advanced chart, then it show me, let me see here. No, I'm not gonna sign in. Just, uh, I remember, oh, here we go. I can make a candle. Why? Oh, 1 minute, let's say 1 day. Here we go. So that I can have a candle chart for this. I'm not sure whether you're familiar with that, but this red means it's, reducing. Gray means it's increasing, and it's high is here, low is here, and for a red line, this is the open, price, and this is a close price. For a green line, this is because it's increasing, so this is open price, this is the, close price, and the high, low, something like that. And correspondingly here, you can see O means open, H means high, L means low, C means close, V means volume. You can see, for example, on this day, April 30th, 2025, the high is 94,000. Sorry, open is 94,000, high is 97. Low is 94, close is 96, volume is 32.9 billion. So this is data. So at least I need to consider this OHLC, open close, open high, low close data and volume, and we may generate some other indicators like, MA moving average, or some different, indicators. So you probably will need to consider a lot of attributes here. But here, for convenience, I just, merge everything to be one axis, and for convenience, so let's assume it's just, 2D. Okay. So now we can just write it. So again here, x-axis means the vector for those inputs or attributes, and this y means the response. Okay, y is 1D, x is has p dimensions. Okay, now the problem is, given those points, those blue points, I can plot infinitively many lines on this p plus one dimensioned xy plane. P plus one is because, again, x represents for p dimensions and y is one dimension. Hence, it's p plus one dimensions. The problem is, how do we decide which line is the best, assuming, it's a linear trend? If I just ask you to check by your eyes here, we have uh the first one is red, second one is blue, third one is green, fourth one is yellow, fifth one is, I don't know what is this color, maybe purple. Let's say purple. Which one would you choose? I believe most people will choose from the red line, right? I guess nobody would really choose the yellow line. But why? Why do you think this red line is the best line? Intuitively, by our eyes, we can just say, hey, it's so, let me just amplify it a little bit. I can just say, hey, it's so simple. Of course, because what? Because this red line is what? Closest, fits this one, two, three, four, five, six, seven, these seven blue points the best, right? I guess nobody would choose the yellow line. If you would prefer to choose the yellow line, you probably need to, visit an eye doctor. Something's wrong, but why, for example, why don't you choose, for example, the green or the blue or the purple line? Why would you choose the red? So we say it's close, but here close is intuitively by our eyes, like directly our vision, checked by vision. For a computer, computer cannot directly like see like us. Actually, to be honest, in our brain, to see something is a very complicated, like a signal process. So what we are doing here, or say machine learning, is we want to render this process by mathematics instead of intuitively, because our brains are like patterns recognition. It's trained itself in the neurals. But here we need to let computers know. And hence, when we say the red line is the closest or is the best to fit these 1, 2, 3, 4, 5, 6, 7 points, we need to define clearly what does best or what does good mean? What does close mean? How close is close? And hence, we need to answer those kind of questions. Say, why is the red line considered the best? Or fundamentally and mathematically, how can we define good? What does good mean, right? And then we say good is close. Okay, again, what does close mean? When we say close, we need to have a way to measure the distance. Is it measured? Let me ask Zoom to forgot like how to. Oh, here. What color? Red color. Let me use the yellow color for. Let me use green color. How close? What does close mean? Is it like this way, or like this way, or like this way? I mean, we need to accurately tell computer what does close mean, and we need to define a metric, right? Meaning a way to measure the distance. So these are all the questions we need to carefully consider and carefully and accurately define and let a computer know. Okay, here we go. So here we use a projection since it's actually no matter which dimension, how many dimensions, the same. So the projection means, so consider this data point. So let's assume this data point is xi, y, sorry, my fault, this. Okay, I'd better be clear here. Let me just ask Zoom to give me more. Okay, here we go. So I want to make it clear. So these, all these are the observed data, okay? And the red line, this line here is the line. I assume this is the line that I want to choose. And then remember before we mentioned here, these are still here. Anyway, we said we need to define a metric, right? And hence, I assume the red line is the linear function I'm gonna choose. And given those 1, 2, 3, 4, 5, 6, the seventh is here. Sorry, I forgot to plot the seventh. The seventh is here. It's these two just overlaps. That overlap. That's why here. Given this seven data, I want to first find a metric. Second, find a way to define the closest or define the best. Okay, so here my metric is I suppose, let's consider this data point I. So its coordinate is xi and yi, where yi is the response and xi is the attributes of data point I. Okay, I project this one onto this predicted line, and I get a corresponding point, which is here. Let me use another. Okay, let me use, let's say, green color. Okay, I project it onto this line. What does project mean? So project here simply means it's let me again plot a line. Just plot a line which is 90 degrees, or perpendicular to the x-axis. This means project. And then let me see, how can I actually don't know how can I erase this drawing here. Let me try to erase it. Okay, here we go. And then I have this yi hat. Yi hat means the predicted response. Why? Because here the xi, right? So here xi are projected onto this line. So I have this point. What is the coordinate of this point? It's xi, yi hat. And hence, this yi hat is my prediction for the data point xi. Now, I use absolute value of yi minus yi hat as the distance. And by this way, let me clear everything. By this way here, I can define a metric here. Get a point? Again, let me repeat this. This is very important. First of all, given all those kind of, observed data, these are the real data, okay, that I observed given this data. Second, I project this data onto the line that I'm choosing. And hence, I get this y, coordinate, and I name it to be yi hat. Clearly, if I choose this line, so the response of xi data point xi will be yi hat. But in most cases, it won't be 100% accurate. There must be an error, right? How to define the error? So we use absolute value of yi minus the true response minus the predicted response to be the error. And this is called the absolute error of data point I. Uh, why do we need to use absolute value? Because think about this, it can be smaller. The predicted data can be bigger than the real yi, which is in this case. Or like in this case, you can see the predicted one is here, while the real one's here, it's smaller. So we use absolute value to show how good it is. So clearly, after adding the absolute operator, it's going to be non-negative. So 0 means accurate. The bigger, the worse. If you do not include this absolute, let's say in these 2 points, they will cancel. Clearly, these 2 points, it does have this error and this error. But if you don't have the absolute, operator here, they will cancel each other. And then it will give you a wrong info saying that, oh, the sum of the error is 0, but it's not. And that's why we need to add the absolute value here. And it's called the absolute error of data I. Okay, now this is for data point I. So I have data point 1, data point 2, data point 3 till data point 7. So to say how good a fitting or a specific line is, I will, first of all, for each data point, instead of calculating the absolute error, I will make the square error. We typically call this yi minus yi hat square the sum. Here the squared errors. The sum means we need to have the sigma, but only let's say yi minus yi hat square, it is squared error. Or you can also call it RSS, which is the residual sum of squares. Typically I just call it sum of error. Typically I just call it squared error. Make it easier, But the formal name is residual error something. And then I have data point 1, data point 2, data point 7 till, and then I sum up all of the squared errors. And so I hope everybody is familiar with this notation, sigma notation. Excuse me, notation. Sigma I from I equals to 1 to from 1 to n means I'm gonna do it y1 minus y1 hat square, and then parenthesis y2 minus y2 hat square until n. Here n equal to 7 because I total have 7 data points. And hence, here I get the sum of squares, which is RSS. So how can we define the best? So here we've already had a metric, right? Okay, so for any given line, I can have a metric, use RSS. Let's say, suppose I have a line, again, give me a line. Let me use another color. Let me just, let me use, let's say this color. Okay, suppose I have this line, for example. So what would you do? Similar things. You can calculate this one, right? You can calculate, okay, this is the projected point. This is a projected point. This is a projected point. This one is here. And whereas this one very small. I mean, I even cannot plot something, but it's almost here. And this one's here. And this one's here. See? Again, I get what I get, 1, 2, 3, 4, 5, 5 here, 6, 7, 7 projected yi hat, right? And then again, I can use the true yi minus the corresponding yi hat squared to get the squared error for each data point. Then I'm going to sum for all these 7 points, and I will get another RSS residual sum of squares, right? Let's say I have a RSS red versus RSS green, then I'm going to compare, see which one is closest, means the total, the sum of the squared errors. Then the one is smaller, the smaller error, the better. And hence, let's say, for example, suppose the red one, the error is smaller than the blue one. Then, sorry, the green one. Then I will choose the red one. So here, recall again that we said we want to choose a line closest to these given data points. So closest can be interpreted to what? To minimize the RSS. So that's the logic here. First of all, I need to define the metric. How to define a metric? I use this yi minus yi hat square. Uh, People may ask, why do you use square? Why don't we just continue using the absolute error? This is because later when we calculate the things, if it's a square, it will be a quadratic function. Then doing optimization to minimize it, we have some specific algorithms, which is just the Lagrange dual method, Lagrange multiplier. It can make our work much easier. That's why we use square instead of use the absolute value. So first of all, I have this metric. Second, given the metric, I want to choose the best. What is the best? The best means to minimize the line, which can minimize the sum of the squared errors. I would consider that line to be the best. Okay, so this is the logic. Okay, now let's define some notations the method to get the mathematical model. So first of all, I have n observed data. These n observed data are let me see. These n observed data are x1, x2 until xn. Be careful again, each data point has p attributes. Okay, p attributes, for example, can be height, weight, gender, those kind of different attributes. Each data has p attributes. So that, for example, x1 gonna be x11, x12, x13, until x1p, x1, xn will be xn1, xn2, blah, 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 xnp. Okay, with corresponding responses, they will be, let me use another color. Oh, I cannot add a color, give me a color. They are y1, y2, yn. So these are the corresponding data responses. Be careful, I said the corresponding means x1 is corresponding to y1, x2 corresponding to y2, xn is corresponding to yn. Okay, now I want to find out a linear function to fit these n data points. So the linear function, it's returning this way: beta 0 plus beta 1 x1 plus beta 2 x2, blah, blah, blah. Given p dimensions, I should have beta p times xp. Or if we want to write in a matrix form, it's simply in this way: beta 0 is a scalar, which is the intercept, and beta is the vector. This T means transpose of the vector, and the x is, x are these axes, x vector. And then clearly the linear function is completely determined by what? By this beta vector and this beta 0 interpreter, the scalar, right? Once I have all the beta, then it's done. So for example, you may get confused. Hey, why here x has two, attributes here, but here it has only one, because this x1 is a vector. So for example, here you can see here I have x1, x2, the xp. I can actually substitute it. I believe, yeah, it's in the next slide. For example, I substitute x1 vector into it. That means what? This x1 becomes x11. Then x2 becomes x12. This xp becomes x1p. Similar thing. I can substitute xn, data point xn. Then this x1 becomes xn1, xn2 till xnp. That's the thing. Okay. In other words, here, let me just remove all the drawings here. In other words, here, I want to find out these parameters, which are beta and the beta 0, such that the RSS is minimized. Okay, let's do it step by step. First of all, I want to substitute these n observed data points into f. F means this function. Okay, so for x1, which is here, so be careful when it's in the bold. That means what? That means it's a vector. Like no bold, that means it's just a scalar. Okay, it has a beta t x1, and x1 is what? As we just mentioned, x1 are x11, x1 to the x1p. So substitute. So you have this line, right? I'd better just let me see, how can I? Okay, so I have this one for x1. Okay, now for x2, I have this. I just simply substitute x2, x21, x2 to the x2n, okay, x2p, sorry. And I do this all for all these n observed data points so that I will have this. And the corresponding yi is, just by this function y, because here I can have y equals to f, these things. So I have the corresponding predicted responses for y1, y2 till yn. Okay, now remember, we define this as a squared error where yi is the true response of data point I, and the yi hat is the predicted by this function y response. And then I squared, okay, then I just substitute y because this y hat equals to what? Equals to this, right? Equals to this one, just substitute it. Okay, so that, but I have the RSS equal to, by the way, here SLR, I guess I forgot something. Let me see. Okay. Here LSLR means least square linear function by name, least square linear function, which means I want the sum of squares to be the least, the minimum, the minimum. And hence I have this LSLR. We want to find the beta vector and the beta zero such that these RSS, such that this RSS is minimized. Be very, very careful. Many people may consider X and Y's are the decision variables. No, X, Y's are known. Okay, these are the known data from from the observed data. By comparison, this is beta 0, beta 1, beta 2, till beta p. These are the real decision variable that you need to determine what should the beta 0, beta 1 till beta p be such that my RSS can be minimized. Mathematically, we can write it this way. This is actually something about optimization, but since we only have 6 weeks, I don't have enough time to talk, this in very details. Just to let you know that mathematically we can write it this way. So argmin means the values. Here, beta and beta zero are the variables, and I want to minimize this thing, which is the RSS. Minimize RSS, and they just RSS equal to what? Equal to sigma I equal to 1 to n, and this square things. Okay, beta hat and beta zero are the minimizers, which means the value. Okay, now the problem is mathematically it's beautiful. Practically, how can we get it? That's actually that's actually the reason why we want to square it. Because by squaring it, it will be a quadratic function. And we can directly make the derivative or the nabla, the gradient to get it. Before let me first introduce the matrix form. So we have already returned, where it is? We've already returned everything here. But as you can see, it's pretty long, pretty big. Is there a way we can write it smaller? Yes, we can. First, we have y1 hat equal to the beta 0 plus beta t x1, and y2 hat equal to beta 0 plus beta t x2, blah, 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 like this. And then we can equivalently write it in this way, where this y hat vector equal to, this y1 hat, y2 hat, which is the left-hand side. Okay. Then the x equal to this. First, the right part of it is simply our observed data, which is x11, xy2, x12 to x1p, which stands for the row vector for data point 1. Then here, row vector for data point 2. Here, the row vector for data point n. Be careful that we also have this part, which is a one vector. So why do we need to have this one vector? Why don't we just define x in this way, which is here, right? Isn't it easier? No, it's not, because we want to include, or we want to absorb this beta zero into this beta vector. And by the definition of matrix multiplication, we do need to have this one. You see what I mean? Remember how to make a matrix matrix multiplication? It's each row by each column, row by column, right? So if I write x beta in this way, let's say the first row will be what? The first row will be first row in the result, I should say, would be 1 times beta 0 plus x11 plus beta 1 plus x12 plus beta 2, blah, 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 plus x1p times beta p. You see, which is exactly this form. And the second line, third line, all the same. And that's why, because we want to include this beta 0 in this beta vector, and hence this first column ones are corresponding to handle this interception beta 0. That's the reason. Be very careful. Don't forget this one. Okay. So this is a matrix form. And after using the matrix form, it's just this equation. Super simple. Y hat equals to X matrix times beta vector. Done. Where the definition of Y hat, X, and beta are here. Okay. So now let's first have a look at an example to see how we can really write it. Say, suppose here I observe the two data, which is x1 equal to this 132, x2 is negative 102. So I write as x dot 1 and x dot 2. That means, x1, where am I? Let me see. I should think this way in this way. Sorry, my fault. I should say explain it in this way. Let me write it down here. So this is x vector 1, x vector 2, x vector 3, and so these three are the observed data points, and each data point has two attributes. Dot x dot 1 is one attribute. Let's say, for example, this is the height, this is the weight. I have two attributes. For x, it's x11 is 1, x12 is negative 1, x21 is 3, x22 is 0, x3 is x31 is 2, x32 is 2. Okay. Now, first of all, suppose we know, we have already known the betas. So that we'll have beta 0, beta 1, beta 2. And later we will calculate it, don't worry. But here I just want to show the expression. And correspondingly, we can calculate the y1 hat, y2 hat, y2 hat, and y3 hat. Again, we will calculate everything in detail later. And the X matrix is what? First of all, you just copy and paste this one, 1, negative 1, 3, 0, 2, 2. And then don't forget here, in the left side, we have a one vector, which is 1, 1, 1. So this is the matrix form in this super simple example. Next, we want to see if we express in no matter, this way or the matrix form this way, how can we calculate the beta? Again, you want to calculate the beta vector and the beta 0 scalar. Okay. Recall, I believe in calculus 2 or calculus 3. First of all, I assume everybody has learned Calc 2 and Calc 3, okay? And then you probably have heard of this, the method of Lagrange multipliers, which is so consider an unconstrained optimization problem. Unconstrained means there's no constraints on beta. Beta can be any real numbers, and the necessary condition of the optimal solution is the gradient or nebula of beta given a nebula of f based on beta equal to 0. 0p means it's a p-dimensioned 0 vector. This means partial f partial beta 0 equal to partial f partial beta 1 blah blah equal to partial f partial beta p equal to 0. If you can recall it, great. If you cannot, not a really big deal because here this is not a math class, but just to let you know, we should have everything 0. And in general, this is a necessary condition. Means, remember what is a necessary condition? Means if I give you an optimal solution, then this optimal solution must satisfy this condition. However, as we define it to be a quadratic function, which is square here, this function is a convex function. And for a convex function, this condition is both necessary and sufficient for a global minimization, for a global minimum. What does it mean? This means this is also a sufficient condition. Means for any point beta, as long as this condition is satisfied, this beta must be the minimizer. In other words, I have this RSS, which is here. Where's the RSS? So this is my RSS, right? in which betas, beta 0 and beta 0, beta 1, the till beta p are the variables. As long as I can find the betas that satisfy this, which is partial RSS partial beta 0 equal to 0, partial RSS partial beta 1 equal to 0, until partial RSS partial beta p equal to 0, then it is this the corresponding beta 0, beta 1, beta blah, blah, beta p must be the minimizer. And that's the reason why here we, do not use the absolute value. Instead, we use the squared value. That's the reason, because it's super easy for us. If we define this way, super easy for us to find the minimizer betas. Okay, in the next step, we're going to calculate what are the partial RSS partial beta 0, partial RSS partial beta p, partial beta 1, partial beta p, like this way. Okay, now let's have a look at it. Okay, first of all, partial RSS partial beta 0. Recall that RSS equal to this. I assume everybody understands the basic calculus. So for example, if I ask you, hey, how to make the derivative with respect to beta 0 in this function, how would you calculate? First of all, you have a -1. Secondly, you have an exponential here. So make a -2 outside here, right? Which is here, -2. And then the others, you just copy and paste. You see what I mean? I assume everybody knows how to make the derivative of RSS with respect to beta 0, okay? So you get this one. And similar things, partial RSS, partial beta j is what? Suppose, whichever beta j there, similar things. You have a -1 here, -2 here in the beginning, and then just copy and paste. But don't forget one thing, that for beta j, it has a corresponding coefficient, which is xij. And hence, it becomes -2 sigma I equal to 1 to n xij, and copy and paste everything. Here, this j can be any number from 1 to p. But here, beta 0 is different. Why? Because beta 0 doesn't have the x0, xi0. It's just the intercept. It's not a coefficient. So, okay, now I just, I have this 0 should equal to this, 0 should equal to this. And now I just reorganize, remove this -2, -2, and reorganize the items. I have these equations. It's called normal equations. So how many equations do I have here? I have one equation, which is here. This is one equation. And I have all p equations. For each j, I have an equation. I have p, totally p such equations. And I have one equation here. So totally, I have p plus 1 equations, right? And how many variables do I have? I have beta 0, beta 1 till beta p. I have p plus 1 variables as well. And hence, p equations to solve p variables. So later you'll see if it's a full rank something, and we should be able to solve it, no problem. So this is the idea of least square linear regression, RSLR. And this solution is called ordinary least squared estimator, OLS estimator. That's the thing. And again, I know I've mentioned many times, be very, very careful here. You are to solve beta 0, beta 1, beta p, okay? Where xij's and yi's are all known. They are the observed data and the observed responses. Don't make it wrong, okay? You are to solve betas, not to solve x's or y's, okay? So first of all, this is, how you can make it. But again, it's gonna be pretty, I cannot write a general form like, in this way, even if this is correct. Why? Because it's just, it's just too complicated. So later you will see here, by a matrix form, I can easily write given a analytic analytic solution here. So first of all, we want to rewrite the RSS in the matrix form, which is this, and then we can write it in the norm form, which is y vector minus y hat vector. And what is y hat? Remember the matrix form? Y hat equal to x beta. And hence I just substitute yx equal to x beta. That's it. Here, 2 norm means nothing, just square the sum of squares, or of all the elements. So for example, just in case, let me give you an example. Let's say, suppose I have a vector 1, 2. So what is the norm of this of 1, 2? This simply equal to, let me use a 3. That's simply equal to 3 square plus 1 square equals to 10. Okay, so recall this is a vector, this is a vector. So the result of y minus xb is gonna be a vector. And then as a vector, you just sum of squares of each element. Done. That's super simple. Okay, now I've defined the norms. Then I want to rewrite it, as a matrix form. So still remember, give me 1 second. I'd better, sorry, I'd better write in the Word document. Still remember, let's say norm of, let me see. I hate it. I hope I can use the latex, which is easy. X vector. This equal to what? This equals x t times x. These are both vectors, okay? Why? Because x is by default, when we say a vector, we mean a column vector, right? So xt is a row vector, x is a column vector. So a row vector times a column vector equals to what? Equals to a scalar or number, right? So that's the thing. So I can say this equal to, like, let's say x1 square xp square. And here we cannot make it bold because these are all the scalars. These axes are the number of scalars. So this finally result a scalar. Okay, similar things. Here I have y minus x beta norm. Let me just copy and paste. Y minus x beta. This equal to what? Similar things, right? I can write in this way, t times itself, which is y minus x beta times itself. And it should also be a scalar. Okay, now remember what we have here. I'm gonna get the nebula, or let's say get the gradient of the f with respect to beta. So I can say RSS equal to beta equal to this. Be careful, beta is a variable. So now I want to do what? I want to get the nebula. Wait, wait. I forgot. Nebula, maybe. Wait, I forgot how do you spell the gradient? Uh, Let me see. I forgot. I remember nebula. How come? That's weird. Anyway, let me try to get this operator. Operators. Yes, I must be here. Uh, where's the nebula? I cannot find this operator. What I mean is this one. Anyway, let me just directly this partial RSS partial beta. Let me just write it this way. Technically, I should write it as nebula. This equals to what? So we need to get a gradient here from this with respect to beta, right? If you're familiar with those vector derivative operations, you can actually directly calculate it. Why? Because here I want to get the beta. So first of all, here I have what? A negative xt. And oh, sorry, negative xt. And then I can just copy and paste y minus x beta. And similar things for the next part. And then, because it's going to be a t. And then this beta, you need to make the dimensions the same. And then what you will see will be the same thing as this. Let me just copy and paste. And this equal to 2 times this. So this will be the result. Or if you are not familiar with that, let me tell you a trick. You can simply write it this way, because you just expand it. y t y, and then what? Minus y t x beta, and then minus beta t x t y. Be careful, okay? X beta t transpose is beta t x t. It's not x t beta t, okay? And then also plus beta t x t x beta. To save my time, but anyway, I can do it. Yeah, make all bold. And then here you have everything. Now you make it a derivative corresponding to beta. It will be much easier. But just to know to let you know, the result is this. Then by the Lagrange multiplier, remember it should be equal to what? Zero. Zero p. Okay, it should be p means the p-dimensional data. And here we go. And then you see what I have this equal to zero. And then I want to ask you, hey, what is beta? You can immediately get what? You can immediately get what? Make this -2 gone and then move this one here, so that I should have beta equals to, let me see, I should have, yes, because I will make this one in, okay. Let me just write it down. Let me just, in case I make any mistakes, let me write in this one. One more step, 0 equals to -2 is going to be gone. So x t y minus x t x theta. It will be in this way. And then it's going to be super simple. Beta equals to what? Beta, of course, equal to x t x inverse, and then x t y. And I believe in the slides, I'm making the tribute beta hat instead of beta. The reasons because, yeah, because, I just want to give it a special notation, you know what I mean? So that I can just define this one to be, I can define this one to be the minimizer, and hence I name it to be beta hat instead of general beta. So we can get this. Okay, now what does everything, before I show this example, I will going to explain one more thing is, here we have a matrix inverse. If you recall the linear algebra that you've learned, it doesn't mean every matrix has an inverse, even for squared matrix. Okay, so first of all, XTX clearly is a squared matrix, right? Why? Because what is the dimension of X? X, the dimension, I remember I wrote it here, as n times p plus 1, right? So xt, the dimension is p plus 1 times n. So a p plus 1 times n times a n times p plus 1. The result is what? Is p plus 1 times p plus 1. And hence, the result of this XTX matrix as p plus 1 time p plus 1 by p plus 1 square matrix. However, it doesn't mean the inverse exists. We write here inverse, or let's say we have here, right? Or I can just make it easier. Ignore this 0 equal to. Yeah. Here, in order to say, hey, what is the beta value? I inverse this one. I time this one in the left, inverse it. I need to guarantee this XTX does exist. Otherwise, no way, we cannot write it this way. So what if, let's say, in a practical problem, this XTX is not full rank, meaning that it's not inversible. We typically can use the regularization method, which will be introduced in the next lecture. We will introduce Lasso and Ridge methods, or we can use the pseudo MP pseudo inverse methods, which is actually a kind of like numerical method to try to avoid this kind of divide by zero, these things, to gradually step by step replace this the denominator zero. That's the thing. But here we assume this inverse exists. Now let's have an example. Remember the previous example we just showed. Now let's calculate the y hat and beta hat in detail. Okay, first of all, we assume my y's are here. Okay, so again, let me just write it down like this way. So this one is my x1. Where's my pencil? Pencil. It's my x1. And this is x2. X2 gonna be in this way. and then x3 gonna be this way. Hat means vector. X3, okay. Then first of all, I can use this formula to get the beta. And then the E is the residue. I believe where did I write? I wrote it here. We calculate the residual as y minus y hat. And then the residual sum of these squares is the RSS. Okay. And then we can calculate the residue. And in this specific example, you will see the residue is almost zero. First of all, let me just run it. I hate to do it. Let's just do it instead of just saying it. Okay, again, my laptop expired, so I downloaded this one, which is a free one. I mean, I personally really love those kind of free open source apps instead of those kind of things. Everything for subscription for money. I really hate it. Okay, so first of all, let me just put it here on the screen so I can copy and paste. So first of all, I have the y equal to negative 1.03, 3.99 and 7.63. Okay, sorry, yeah. Let me just show why. Okay, so this shows why indeed is a column vector. Okay, now let's put the X matrix here. Recall that X matrix, the left side is always a one. Okay, so it will be 1, 1, negative 1, 1, 1, negative 1. So the second row, third row gonna be 1, 3, 0, 1, 2, 2. 1, 3, 0, 1, 2, 2. The first column is always here. The first column, because this is inverse x. Not inverse, this is transpose x. This is x. The first column is always one, okay? So that I have 1, 3, 0, and 1, 2, 2. Okay, so let's have a look. Okay, indeed this is okay. Now remember, beta, I don't know, beta hat equals to what? Should equal to this formula, inverse of x transpose x times x transpose times y. Okay, now let me just put it. The inverse of x transpose times, you can, if you have used the MATLAB before, you can see everything's actually the same as MATLAB, times x inverse times y. Here we go. And then we have this this result, 0.15, 1.28, 2.46. It should be the same. Here we go. You see what I mean? Okay, now I have this. I can calculate the residual so that I can calculate, let me calculate y hat. What is y hat? Remember, y hat is nothing but beta x times this correct calculated beta hat. So equal to x times beta hat. Okay, this is the y hat. And now I can calculate what? Y minus the true response minus the predicted response. E equals to y minus y hat. And you see the numbers extremely small, right? Are they the same? Look similar. Okay. This is a 10 to the power 15 minus this. It's almost zero. I mean, I use a bold zero means a bold zero vector. Oh, this shows that the prediction is so good, right? However, you can see I use double quotation to good. Later, you will learn that this is a phenomenon called overfitting. This is too good to be considered good. I know this is a bit confusing. In general, it's not good. It's not good because this overfitting means your fitting gonna be something like a cheating that your fitting gonna only works perfectly for the training data, while for the future data or for practical data, it may not work well. It's called overfitting. No worry. Later we'll see overfitting a lot, and then you will learn different methods to try to eliminate this thing. Okay. So this is an example. How can we use these normal equations and the OLS, the ordinary least square estimator to get the results? And again, once my betas are known, my function is known. Then done, everything is done. That's it. Okay. Then the next one is one thing, which is the quality of fitting. How can I know the quality of a fitting? Right? Say I have different fittings. How to judge which one is the best? First of all, we can use the coefficient of determination, which is r squared. It's calculated by this one, r squared equal to 1 minus RSS divided by SS total. The SS total means the total sum of squares, which is given by this. It's nothing, just the squares of, 1i minus y bar. That's it. Y bar is what? Y bar is wait a minute. Yeah, y bar is the average of the observed responses. So this is y bar. And again, y bar, this y bar vector means, for each element, all the element, the value is y bar, y bar, y bar. That's the meaning. Okay. So in general, or let's say in many practical cases, a linear regression with r squared is greater than 0.8 is considered to be good. Greater than 0.5 is considered to be okay or acceptable. However, be careful. This is just like general speaking. For different examples, you cannot necessarily claim this. In some cases, honestly, even if r squared is less than 0.5, the linear model can be considered to be good. Okay, so now let's see how can we do this in Python. Uh, First of all, I introduced all this. That means technically you can code it by yourself how to run this. However, it may be very time consuming. And recall, why do we use Python in data mining? Because there are a lot of existing libraries, right? So we want to be lazy. We don't have to redo the jobs, the jobs that have already done by many other people again and again. Hence, we use libraries. So here we will use the scikit-learn. Where's the scikit-learn? Scikit-learn library here. But anyway, let me just start the Jupyter notebook to play this. Bitcoin. Well, it's reducing again. Great. Oops. Okay, looks like if someone invests in Bitcoin, gonna lose. But anyway, no worry. We'll use machine learning if we have time again. We will use machine learning models and coding methods to train an automatic algorithm to make different predictions and different actions and try to make an automatic trading system. But anyway, let's first play this thing. Where's my data? Oh, data's here. So if you go to lecture 3, you will see a lecture, you will see a folder called the data. So I put all the data here, okay? So let's go to Jupyter Notebook. Sorry, ignore it. This is something that just, uh, why it doesn't? Oh, yeah, correct. Because I have not. Let me create a folder lecture 3, linear regression 1. Okay, now let me create a new Jupyter file. Let's call it, rename, in class lecture 2. Okay. And then I will need to pass those data here. Let's say create a new folder. Let's say data folder. And now I'm gonna download. For you just you just download. Click this one, download, and then you have all the data. Okay. So here, since I've already have everything, so I'm not gonna download. What I'm gonna do is that I'm gonna directly pull all this. So these 3 files are my data. I just directly drag them here. Wait 1 minute. I'd better drag them in the data folder. Yes. So that I will just drag these folders here. Done. That's going to be updated. Last modified next year. Oh, that's so interesting. Okay. Uh, let's go go back to my what? Go back to my notebook here. First of all, let me make it bigger. Increase, increase. And then second one, let me put the line numbers. Okay, so now we are here. We want to see how can we do this. To do this, we need to actually handle several steps. The very first step is to load the data. So we'll execute this. Let me just save this one here so I can close it. Okay, so I'm gonna have import numpy as np. By the way, again, numpy is something to handle those kind of array or matrix related things. And indeed, here we will need it, trust me. And the second thing is to import pandas as PD. Pandas, as remember, is called I personally call it Excel. the Excel in those kind of data, data mining or those kind of codings, because that will handle those kind of CSV, those kind of data. And then I'm gonna have a data equals to PD pandas dot read CSV. And then I'm gonna have this. Remember where we save it? Well, let me make it bigger. I forgot what's the name. 2D. Here's. I just want to copy and paste. That's it. So I saved it here. I saved it under this. So first of all, this notebook file is here, and you can see this is under the same directory, but this is a data folder. So here we can just call it data. Let's say linear, like this way. Or for example, suppose your data. Suppose okay, this one is direct. Let me just drag one here, just make it easier. Suppose this one is directly here. Then you don't have to have this data because they are under the same directory. You see what I mean? No worry, we'll run it and then we will do different examples. Let me see, delete it. Okay. So now let's make this one, and then we can simply just put the data. You even don't need to put a print, and then it will show you. Okay. And then meanwhile, because I do have this in my Excel, so that I can just and this is actual data. I have a response Y and I have X1. This is 2D to make my life easier. How many do I have? I have 100 data. You can see count 100. Okay, so they're the same here. And in Python, the index starts from 0, so it's from 0 to 99 instead of from 1 to 100. This is the thing. Okay, now let's do this. Suppose I don't have data, folder. After I say this, it will show you error. It will tell you that, hey, there's no such file. Why? Because it's another one. Of course, if I just put it here and I rerun it again, and it will show correct. You see what I mean? Okay, so this is just to show you how to control those kind of things. But here, let me just delete it. Okay, so this is a way for us to actually load the data. So the next thing, what we want to do is we want to load the X and Y, because this data is just it's a combination of both X and Y. So what I can do here is X equal to data dot job columns equal to Y. This Y is this Y. So for example, if it's called YYY, then you're going to call it YYY. You see what I mean? Because here is the citation of the column name. The column name here is Y. So X equal to data job. Remember, this is data job Y. What do we have? We have only X1 here. Because here, this X is only one column, okay, in the first example. And hence, you can just, you can just print X. And you can see here, X is this way. See it? So this is the thing. I remember I wrote something here, which are a different thing, well, different like commands for writing this. So for example, if you want to drop multiple lines here, you can just write columns equal to Y, X1. So, you can include all of them. And here, wait a minute, I realized one thing. I forgot to write this axis. But axis by default is actually to drop a column, so that even if I didn't write this one, it's correct. So technically, I should add axis equal to 1. This axis equal to 1, that means, remember we have the drop method. This drop is to drop a column instead of to drop a row. Column equal to 0, axis equal to 0 means we are gonna drop a row. Later we'll see it. Classic no, which one PCA or which lecture you will see we will drop rows as well. And you can equivalently write it in this way. Here, instead of columns, we're gonna say data dot columns 0. That means what? That means we'll. Oh, sorry, my fault. That's why I realized. Sorry, my fault. I should have put a 60, not 2D here. So sorry. Let me just comment to this one. Let me show you the whole data. Sorry. So this is a Y and then X6. So let me open the correct document. Oh my God, everything's wrong here. 6. Okay. In this example, this is the data that I should discuss. Sorry about this. So it has 6 attributes and one response. And as you can see, it should be 100 lines, 100 rows. Yeah, and it's actually 100 rows, and then similar things. You can see it's from 0 to 99. And then we can all use here x equals to data.job columns equal to y, and hence you can see the y columns job and this is x. You can, for example, also say job columns y and x2, and then you can see x2 is gone. So your x equal to x1, x3, x4, x5, x6. That's a thing. Okay. You can equivalently write it in this way instead of directly give the name of each column. You can write data.column, and then here you're gonna have, let's say, column 0, and you sorry, forgot to delete this. And you can see again the what is gone, the y is gone. See, or if you have multiple, be careful. You cannot write in this way. It will show you error. Instead, you need to write this way. And then you see x1 is gone, or you can say x3. So in this way, it will include x1, x2, x4, x5, x6. 1, 2, 4, 5, 6. See it? X3 is gone. You can write it in this way as well. So this is just the corresponding, you use the corresponding column number. And the previous way that I used is the absolute name of the column, the corresponding column names. They're the same thing. Okay, so now after this, now I've already got X matrix, right? Which we jump Y. Next, we'll get to the Y matrix or Y vector, I should say, not matrix, because Y is just a column of the response. And I can write in this way, Y equal to data Y. Done. That's it. Super simple. And then, uh, uh, I forgot to cover it. And then if you want to have a look at Y, here we go. So this is Y, and you can see it should be the same. It should be the same as these numbers. See it? The same thing. Okay. Similarly, you say, hey, I don't want to use this, right? You can just use this method. Let's say, remember data dot column method, data dot columns 0, and it will be the same. Sorry, forgot this, and it will be the same. I personally prefer to use this method because it's just easier. I don't have to. I always make those kind of brackets wrong something, and typically those names are easier. However, be careful. Like in some data sources, the name could be super long. If the name is super long and it's not easy for you to copy and paste, you are lazy to do this. Then you can just use data.column and then use the other methods that I just mentioned. Everything can be found in the slides. You can use this method to get the index. Okay. Now we will do what? Now we already have X and Y. We will need to train the data. So there are 3 types of data in machine learning typically. The first group of data or the first data set is called training data. Training data is used during the training process to fit the model parameters. For example, in linear regression, the model parameters are the intercept and the coefficients, which are beta 0, and then the coefficients are beta 1 till beta p. Okay, then the second data set is validation data. Validation data is used to tune the hyperparameters, which are the parameters that controls the learning process. They are not directly learned from the training data. After linear regression, you will learn something called a k-nearest neighbor, KNN, in which this k is actually a hyperparameter, and we will use validation methods, validation data to tune this k parameter, hyperparameter. And the validation data sometimes also helps avoid overfitting. And this is mainly used for model selection. In the I don't know which lecture, but later you will have a lecture talking about this, which is a cross selection methods. And then techniques, something cross validation. Sorry, techniques related are from cross validation, which is something we're going to introduce in I forgot which lecture, but a future lecture. Bootstrap is another thing, which is just you get it and then put back, get it, put back, So these are two different things. And the third data set is called test data. Test data is used to provide a final evaluation of the training and the tuned model. And it's usually independent of both training and the validation data sets, and it can provide an unbiased estimate of the model's performances. So, for example, suppose in this example, we have how many data? We have 100 data, right? We have totally 100 data. So what we're going to do is that we will split it into, let's say, for example, 30% to be the training, test data, 70% to be the training data here. And you may ask, so where's the validation data? You said it 3 data sets, but just now you just said 70% of training data, 30% of the test data. We don't need the validation data in this specific example. Why? Because we don't have the hyperparameters. That's the reason. Okay. Again, later in KNN, you will see what does the hyperparameter mean and why do we need to tune it. Okay, so in this specific example, I don't have to do it. Now let me, in the next cell, I'm going to import the scikit-learn library. This is sklearn. The scikit-learn library is a small, concise, but a very, very powerful machine learning library. It's pretty relatively fast, and it's just very simple and concise. sklearn import linear model. Okay, here we go. Okay, now we can do is first to split the data X train, X test, Y train, Y test equal to sklearn dot model selection. Wait a minute. I need to have a look. Sorry, I forgot. I guess yeah. Model selection dot train test split dot model. Okay, good. And train test split and then X Y. If you cannot remember, you can press Shift in the table. Oh, Shift in the table. It doesn't show me anything, or you can just kind of paste this one and Google it. And I bet you can directly find the documentation. Here we go. See it? But in many cases, I'm lazy. I just press Shift table. It doesn't work anyway. It will show you some simple documentation so that you can learn. But here, what you're gonna do is have a parameter called the text size, test size equal to 0.3. So this means I will remember we have already got X and Y here, right? So I will split this XY to be two groups of data sets. Data set number one is called the X train versus and the Y train. These are the training data. And the data set number two is X test and the Y test. There are the test data. And the size of the test data gonna be 30%, 0.3. So this is the meaning. I can definitely after just print from X train, or I just and here we go. This is X train. And indeed, you can see 7 rows, 5 columns. Well, why 5 columns? Wait. Something is wrong. Sorry. Oh, sorry. My fault. Actually, I forgot to. I need to rerun it. Sorry, is it wrong? Okay, so X, now it should be 6 rows instead of 5 rows. Yes, 6 rows. And indeed, because we set test data size to be 30%, and we totally have 100 data. So of course, for the training, you should have 70%, which is 70 data, right? And 6 columns, which are X1 to X6, X train. And be careful because they are randomly selected. And hence, if you run different times, all these data will be different. Again, this is the original index of the data, okay? Remember, let me just show X. And the original indices were from 0 to 99. And this is, we can remember, for example, the first one is 96, the last one is 26. And if I run it again, I bet you they're different. See? Why? Because here, scikit-learn.model selection.train test split, it's a random selection to eliminate the bias. And hence, every time you run it, the training data will be different. Similar things I can say test, I can get the Y test. Y test is here. And you can, get it for X train, X test, Y test. as well. Give me 1 second. Let me do it this way. So let me use another cell because otherwise, if I have this one and every time I run it, it will be very different. You see what I mean? Because every time it will run the whole cell and it will repeat this code. Then let me use another code. Let's say I'm going to say, hey, what is X train? Show me X train. It's here. So your rank again will always be here. It won't be changed. Why? Because I'm not gonna run this line. That's the reason. Okay. And then I can say what is Y train, the corresponding Y train. Recall these indices 94, 16, 90, and then you will see the same 94, 16, 90 seed because they are the corresponding Y responses. Okay. Similar things. Let's say X test. Okay, these are X tests. Totally should be 30. It doesn't even show me the size. I can say X test the size 180. Uh, and 180 is because I have what I have 6 rows and six columns, and then after it will be Y test. Here we go. So these are 30, data. These are the X train, Y train, X train, X test, Y train, Y test, the data. Okay, now what we can do is to train the model. Okay, so to train the model is actually pretty simple. We're gonna run this way, which is model dot uh, let me use this cell. Let me create a new cell. Model equal to linear model dot let me see. I believe it's no big. Yes, big L. Linear regression. This is what to set the model to be linear regression model. And now I'm gonna delta say model dot fit. So recall that we showed so many steps of mathematical, like mathematical formulas, derivatives, something like this, and then we get all these OLS estimated right. While you are writing the code, you just need to write a model of it, and everything will be done automatically. X train, X train. Be careful here. X train, Y train, all the training data. So this means you are going to fit the model by X train or Y train. Don't use X test, okay? Because these X tests were the test data. These are the training data. And the model is linear model dot linear regression. So this model itself, Python already knows it's a linear regression model. Okay. After fitting, I can just calculate the R square equal to model dot score. Remember the coefficient of determination, X train, Y train. Okay. So that so that's R square. So now I can actually print the results already. Print, let's say, the fitting R square is R2. The intercept beta 0 is beta 0. Be careful here, I cannot write beta 0. It's called a model intercept, model dot intercept. Print the coefficients beta 1. I have beta 6 actually. Yes. Big 6 R model dot I believe coefficient. Yeah, this is the same. So now you will see everything. Here we go. And I believe in my slides I should have something else. Let me. Okay. Dot shape. I forgot. So here you don't have to write 6 because here I remember I remember it has 6 attributes. But what if you what if we cannot remember it? It's actually pretty simple. We can use X dot shape 1. So X dot shape 1 means how many columns it is. You can, for example, let's say I can say print X dot shape. you're gonna see it is 106. That means X total has 100 rows and 6 columns. Sorry, it's not X. I should say X train. Give me one second. Give me one second. It's not it's not this one. It should have yes, correct, because X is my training data as well. So the X is my total data. So the total data, the columns, which is all of them, it doesn't matter your X train or X test, but your total, no matter which one, you totally have X 6 attributes, and hence X dot shape one means I'm gonna get this number, which is the number of columns of X matrix are this. And then you can see here the same result. Okay. One thing is that you may feel here, oh my goodness, it's so long. And also like here, actually, who cares? I just need a from 3.67 down, right? 1.96. Is there a way I can write it to be these numbers like to a more concise format? And the answer is yes. Here I showed you can use those print in the printf. You can use this column dot how many f or something. You can use this one to control it. So for example, here we have suppose a is this number. I have printf a column dot 2f. That means show two float digits. Dot three, that means the three effective digits. Dot one means one effective digits, and these are the corresponding things. Okay, so we can actually change it here. So for example, I want to show 4 digits of the R square, float digits, and I want to show 3 digits for beta zero, and I want to show 3 float digits for NP, let's say beta one to beta 6. Be careful. This one here gonna change the settings for all NP dot array, ND array things. So I'd better just write it here. What I mean here. So for example, for R2, I'm gonna write it this way: R2 column dot 4f. This gonna show for float digits. And then here, intercept, I can still do the same. Why? Because all these are scalars. They're, each of them is a number. It's not a matrix or array. Here I can make it, I forgot how many digits, 3 digits, right? Yeah, 3 digits. I'm gonna here show 3f, several thing. But here, so first of all, let me try it. Okay, so you can see indeed here 4 digits, here 3 digits. Here, can we write it in this way? Let's say how many again? 3, right? 3. Okay. Can I write it in this way again? No, it will show you an error. Why? Because unformatted. This is kind of like this is an array. I cannot write it in this way. So for example, I can just print, let's say model.coef type of this. And you're gonna see it's a numpy.nd array. So it's an array. Array doesn't have this, this one, this method. So what we can do is here mp.set print, let me see, okay, print options, and then precision equal to 3. That means, hey, for all future ND this numpy arrays, just show 3 float digits. And then if you run it again, it will show, see, 3 float digits. So here is the result. I've already calculated the R square, calculated the intercept and the coefficients. That's it. And the next step is what you may want to say, hey, so this is the result, but how about the test data? Remember, we split the data to be 70% of the training data, 30% of test data, right? And by the definition of test data, I want to provide a final evaluation of the trained model, and I want to see how good or how bad the result is, right? And hence, you probably want to compare in the test data set, you want to compare the true response versus the predicted response. So we can do it this way. Y predict equals to model.predict. You see, everything has already been included in the Sky in the scikit-learn library. So you don't have to rewrite the code again. That's why. So I'm gonna do the X-test because X-test is the test data sets that we want to compare. So now I'm gonna compare for each one. What I want to do is that I want to print the true response of the test data versus the predicted response. So this is what I want to do. Print, let's say true response, which is uh, here I'm gonna write a pseudocode because this will be all wrong. You will see later, and I will tell you why this is wrong. Let's say data I versus for all I, in test. Again, this is a pseudo data, pseudo code. This is wrong in test data. I wanna do like this way. Print this, and also the true response versus a predicted response. I want to do something like that. You know what I mean? And now what can I do? Predicted response is what predict I. I want to do this. But we need to make it correct. So you cannot say for all. You're gonna say for, let's say I in all this, how to say, remember the range function? Range of y predict range of length of y predict, not y predict. Okay, so the length of y predict is gonna tell you how long it is. Although we know it is 30, but assuming we don't know, you don't have to manually change. You run the length function. Because later, what if you change your data? So y predict now, for example, is 50. You cannot just change it again. You know what I mean? It will make your code very easy to be run. But use the length function, it doesn't matter how long it is. It can always calculate the length of it. Okay. This one, and then I'm gonna print the response here and actual response test data. I bet you this will be wrong because of this. We can run it. Okay, and sorry, indentation. Okay, very good. Run is correct. So it will show you. Let me see the following. It doesn't show the error. That's interesting. Exception. Let me see why. Okay, it shows you this one is wrong. And then why this is wrong, it should show you. Okay, but I can directly tell you the reason why because of we can see this print type of y test. It will show you pandas core series, and this means actually y test is a kind of like pandas series format type, and hence to show its value, we cannot directly say, hey, y test I, which is kind of like a method for or index method for list. You need to do this I locate. That means I'm gonna locate the corresponding located, which is the i's. Uh, maybe I should make it this way, y test. Okay, you're gonna see this is a y test. See it? Be careful. It has a location index number. The I located means, hey, you don't you, let's say I locate, let's say for example, this I equal to 0, right? That means it's this one. I located doesn't mean you are gonna find the index with 0. Instead, I located means the absolute locate here, given this is the zeros, this is the first, this is the second, okay? This is the meaning. Okay, and then what I can do is make it I locate here, predict response. Now I should have, no, the prediction is so ugly. First of all, you can see after you using I locate, it does show only 3 digits. Why? Because we've already set here. That's why it's a 3 digits. But here I can make it a still .3f. Okay, now it's more beautiful. And here we go. And you can see the results. What is the R square, by the way? The R square is 0.72. Not a very good one, but here are the results. And in the next lecture, you want to see, we can actually plot it. And we can have a comparison actually. So this is a rough example or simple example of how can we make everything. Okay, no worry, we'll have a final summary later of the code. But let's have a look here. These 5 steps can summarize, what we did in Python. First, we're gonna load the data. Second, we get the observation matrix X and the corresponding vector Y. Third, we split the data into 2 parts. Here, 3 mean, validation. Here, in this specific example, I only need to split it into 2 parts. Give me 1 second. Okay, I only need to split it into two parts, training and the test data sets. Step number four is to fit the model using the training data. Number five is to make predictions on the test data sets. And this is all together. Let me just make it. No, I close it. Okay, let me use a new one. So first of all, I'm gonna import all the four libraries. Remember what we did? Import NumPy as MP, import pandas as PD, and then import sklearn, and then from sklearn, uh, import linear model. Okay, first loading data. What do? We use data equal to PD dot read CSV. Remember it? Read CSV. And then, I'm not gonna copy and paste that because otherwise I really want to copy and paste. Just make a lazy rename here. Dot CSV. Okay. And then step number two is what to get the observed X and Y, right? Getting the observation matrix, getting the observation matrix X and the corresponding response matrix Y. Vector, I should say, vector Y. Okay, how do we do it? We set X equal to data.job column, columns equals to Y. Axis equal to 1. Because of what? Because let me see whether I can show the data. No, I don't. Let me show. Okay. Because of this, so oh no, so 60, that's why. Right? And hence I just need to drop uh I just need to drop the Y and the Y equal to the data Y directors, which is the easiest. Okay. Now the third step is what? In the third step, I need to split the data, right? So split the data into training data set and the test data set. Okay, so what did we do? X train, Y train, X train, Y X test, Y train, Y test equal to sklearn dot models selection dot train test split, and then X, Y, and then test size equal to 0.3. Okay. Uh, you don't have to really make it 0.3. You can make it 0.2, whatever. Just, I try to make it consistent, and hence I make it 0.3. Okay, number four is what? To fit the model using the training data. Okay, how to fit it? This is the easiest model equal to linear model dot fit. And, wait, sorry. Linear model dot linear regression should be this. And then model dot fit. And then you're going to use X train and Y train to fit, right? And then you're going to calculate the R2 equal to model dot score, and then X train, Y train. So now you can print the R2 model, which is to print the fitting R square is R2. R2 dot, how, how many digits I reserved here? 4. Equal to 4F. That's it. So now I can do this. And then again, every time I run it, it will be different. Why? Because of this. Every time your X train, Y train will be different. Print this, and then you can do what? You can do print F the intercept beta 0 as 3 digits, and then you're gonna print the coefficients data 1 beta 6. Again, let me not use x dot shape 1. So this shows the column R model dot coefficients. Okay. And then recall that we better add this one empty dot set precision. It doesn't show set print options option. Let me see, I forgot. Print options precision equals to 3 here. Then it will show you everything, the coefficients here, the thing, right? And finally, to make the predictions on the test data set. So I'm gonna first get the y prediction equal to model dot predict x test. Okay, now for each predicted test, I want to show the comparison, which is for I in range of length of y predict print true response gonna be y test dot ilog. Don't directly use y test I, okay? It will be wrong. It needs ilog. Why? Because pandas core series. That's the reason why. And predicted response. The predicted response would be what? Would simply be y predict I dot how many f? Dot 3f probably. And that's all. Okay, so in this run, this final run, the fitting R square is 74%, not too bad. Beta 0 is this one. Beta 1 to beta 6 are these numbers. And here are the comparisons on the test data set of, I can actually make it this way. Print, let's say, I plus 1 data point. I can print in this one. Okay. So first data point till 30th data point. True response are these. And again, every time you run, it's different. The results are different, which is correct. Why? Because of this. Okay. We randomly select 70 data to be training data sets and 30 data points to be the test data points. And here we go. That's everything for a very simple example of this. Any questions so far? Uh-oh, I saw there's one. So a question I want to ask if I want to be notified when files are uploaded on. Yes. Sorry, I just saw your question about 38 minutes ago. So first of all, yes, assignments and exams. If I upload it, I will write everyone an email about this. So you will be notified. Yes. Again, later, if you want to ask a question, you can directly unmute yourself because I typically don't have a look at the chats here. In the chats can cause the answer to be very late, okay? And any other questions about this part, which is how to use Python or scikit-learn library to run the linear regression instead of writing everything by yourself? No? Okay, then we've already finished the linear regression 1. We can have a quick look at the next topic, which is lecture 4, data visualization. And after, why, for example, this lecture is called a linear regression 1 because there's a linear regression 2 after it, which would be in lecture 5. However, you will need to learn this data visualization first because in linear regression 2, I will show you different examples and then I want to make this to be visualized and hence we need this, okay? So let me just close this one and then where's my lecture 4? I will need to open lecture 4 here. Okay. So here, I currently included in only 16 slides. It will be expanded because I just realized that, oh my God, I forgot to include the 3D plots. I just included the 2D plots. First, very simple things. what is data visualization? So data visualization is just to show you, to plot a graphic. They are just a graphic representation of data, or I should say data points. It helps to convey info clearly and efficiently, so we can directly see by our eyes, and our brain can directly process it, give us a comprehensive view of the data. And we typically can only, plot the data to up to 3D. However, we can represent higher dimensional data using some techniques, for example, using different line styles, or using different color or markers group, or layering those kind of techniques to make us to show data more than 3 dimensions. But technically, just without those kind of tricks, technically we can only show up to 3D. The primary goal of data visualization is to help us understand and interpret the data more easily, and making patterns, trends, those kind of things more apparent. And we actually have different libraries in Python, like Matplotlib, Seaborn, Manim, and ggplot. In this lecture, we will mainly introduce Matplotlib. And if you're a fan of mathematics, you probably have seen there is there's a very famous guy. I forgot, because this, if I remember correctly, this is the thing he attribute. He contributed. Uh, where are his videos? This guy. I forgot what is. Let me see. This is his channel. Yeah, three blue, one brown. And as a mathematical like channel, you cannot believe he already has 7.32 million subscribers in the world, which is huge. And I believe he's the main one, at least one of the person who wrote this, this Manim, the library here, this library. And if you have seen his, those kind of videos before, you're gonna see how amazing those kind of I can just randomly choose one to show how amazing those kind of animations are. And really, I wish, for example, we can see here this one, and also the one here. You see the tracks here. These were all plotted by actually this uh, library, Manim. And if we have time, we can really show something here. But anyway, this 6 week super short course, I don't have time. Just to let you know, if you are interested, you can you can just search the documentation of it, and then you can just learn it by yourself. It's actually super clear, and that's really beautiful. Makes mathematical learning way easier than the traditional method, which is reading books or something. Okay, so in this lecture, we will focus in Matplotlib, and actually in the whole course, we'll focus. When we use a plot, we use Matplotlib. Okay, so let's start with the very basic things, which is I need to have a new folder, lecture 4. What's the name? Data visualization, if I remember correctly. Yeah, data visualization by Matplotlib. Oh, which? Okay. Or first of all, I want to show the line numbers again. So here, gonna show you, the basic things how to plot this. So for example, first of all, I need to plot, I need to import matplotlib dot pyplot as plt. Then I can plot some different numbers. Okay, let me make it here so that I can just cheat. It's gonna be easier for me to cheat. -2, 3, 1, 5, and sorry, I don't need this one. And then 1, 3, 8, -4. And then I can plot this, and then I can just plt dot title. I can say plot one. This is just to give it a title, and plt dot x label, which is to name the x label, and then plt dot y label, which is to name the y label, and then finally plt dot show. Here we go. Okay. And so this is x label, or you can say xxx. It really don't matter, you know. So you can see xxxyy here as the name of x label and y label. And also the title is plot one here. And then plt.show will show this. So this is just very simple. And be careful here. This means x1 equals to -2, y1 equals to 1. And here you can see, let me just show. You can see this point, you see it? It's -2 and 1. And the second point would be 3 and 3. And then which is this point, 3 and 3. And the third point is going to be 1 and 8. 1, 8. Last point is going to be 5, -4. 5, -4. Here we go. And I believe in the slides, let me move here. I must have mentioned that by default, it's just kind of like to connect those kind of points with lines, and because here we didn't provide options here. Here's X array. Here is you can see the syntax X array, Y array options. I didn't provide any options here, and hence it's gonna just connect those four lines, those 4 points with lines. However, if we add those kind of points, those kind of options here, it will be different. So in the next slide, I use the option Rx, for example. If I put Rx, then you're gonna see R means red, X means I'm gonna use those markers to be X. I don't have to use Rx, I can use RL, and they're gonna be points. You see, I can use even triangle, those kind of things. You this is greater than, and then it will be those triangles. I can use different directions of triangle. You see, they're different. So once you use those options, it will be different. And also here, I believe, okay, also I make an X limit, Y limit. This means X limit, Y limit. This is to specify, instead of let Python choose it by itself, here I want to specify the display range or display limit of x-axis and y. I haven't, I copied and paste, I forgot to change it, and a y-axis. So here, let me make it to be plot 2. Let me make it an x label, y label, and then here what I'm gonna have is plt.xlim to be let me see, -6 to +6, -6 to +6, and the plt.ylim, I remember it's -6 to 10. And hence you can see it? I force Python to show the x limit to be -6 to +6, and force Python to show the y limit to be -6 to +6, +10. So this is the thing here. And the next thing is to plot those functions. And then here I actually define 3 functions, which is the first function as y equals to 0.2x. The second one is 0. Let me just open the cheating mode and then let me just write it. One thing is that since I've already import matplotlib.pyplot as PLT, so here and this cell has already been executed. So here I don't have to execute, or I don't have to import this again. You see what I mean? And here, let me just import them. Actually, I believe NumPy I've already, no, here's the lecture 4. Here I've never import, see, this is the only cell I've run before. So I've never imported NumPy before. I've only imported NumPy in the other one, in lecture 3, remember? We've imported NumPy here. But here in lecture, oh, what? Sorry, my fault. It should be renamed to be in class lecture 3 instead of lecture 2. That's why. Yeah. we've never run it in lecture 4. That's the thing. So in lecture 4, I do need to import NumPy as MP. Okay, and now I can just here use a command. Oh, I dragged it here, sorry. I can use a command called import NumPy as MP called NP link space. Link space means I'm going to create a linear space. And I can just have x equal to mp dot link space negative 10, 10, 41. So this means I want to create a linear space from negative 10 to positive 10, and I will get 41 points. And Python will calculate itself. So for example, I can just print x. And you can see indeed, negative 10, negative 9.5 till positive 10. You see it? It includes, you can calculate, count it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 times 3, 36, 1, 2, 3, 4, 5, 5. And hence it is actually 41 points. Okay, so now I have this x. I want to plot those functions, plt.plot first x, and the first function 0.2 times x. I can make from whole r this. And the second function is 0 again because I dragged I dragged this PDF to another screen, so you know I can directly read it. Otherwise I cannot remember. 0.03 times x square. Make it to be green for the points, and then x np dot sign. This is a sign function, and it's gonna be b and this notation, and we can just plot it. Oh, sorry, technically I should write plt dot show. Okay, here we go, and you can see this red, you know, this one dash dash. This is a dash point in red, and the second one is a quadratic function, and this is the green square. GS means green square, and they are here. And the third one is a sine function. It is here. And it's a blue and a triangle, but the triangle direction is up, you know, the up direction. And here we go. We did like this way. And to be honest, when you are writing in practice, you'd better not to writing this way. You'd better writing this way. Y1, oops, define Y1 equals to this. Y1, and I'm gonna plot Y1. And define Y2 equals, oh, sorry, this. And define Y2 equals to this one. And then here I'm gonna have y2 and have y3 equal to mp dot sine x. Here's y3. The result is of course the same, but what's the point? The point is here, if you don't define, so later, what if, for example, you want to define different functions or you want to make a change? So you just change here. It will be easier instead, you know, then you change for every place at each plot because you could have several plots instead of one plot. So that's why if you define it in functions, it will be easier. And these are here. These are, you know, I mentioned it here. Okay, so the next thing is how to add a legend. Uh, to add a legend, you just in the options here, remember the options, you're gonna add something, use a keyword label. I actually don't know why it's called label instead of legend. I hope it's called legend, will be easier, right? But unfortunately, it's called labels. Okay, and let me just do it. Let me just use another cell. So we have this. The thing is that if you include these kind of keywords, you cannot like here, you know, you plot three functions all together in one line. No, you cannot. Once you have label function, you have to, for each plot, you need to make it in one line. So it will be 3 lines. So you will have, let's say here, this one will be, let's say the linear function label equal to linear function, and then you will close it, and I have another plt.plot xy2, and then here label equals to quadratic function, quadratic function, and then plt dot plot x3, and then here label equals to sine function. Okay, here we go. Oh, by the way, you need to, that's a mistake myself always make. You need to write this plt.legend. Otherwise, the legend won't be shown. plt.legend. Now the legend is showed a linear function, quadratic function, sine function. And in the example, you can get a title plot for as well. So let me just add a title. Okay, here we go. The order of all these, it doesn't matter. You can write, for example, you can write, legend first, title, it really doesn't matter. But make sure the last one is always plt.show so that it will, show you correctly without a return value. Okay, so this is how can we add the legend. The next one, let's do something romantic. Plot a heart curve. So this is the polar equation of a heart curve, which is rho theta equal to 1 minus sine theta. And it shall show you this way. By the way, here I wrote a footnote, which is it has a romantic love story related here. So in the 17th century, Descartes. So this is the person who invented our coordinates of plotting, which is x and y. So this is the person who invented this xy coordinate. And at that time, he fall in love with princess of, I believe, Sweden princess. However, at that time, because Descartes, he's just a poor mathematician. So the princess dad, which is was the king, tried to stop them, stop their relationship. So he stopped, like the princess wrote those kind of love letters with the mathematician. And later she said, "Hey, we just want to discuss mathematics. Can I just discuss mathematics with the guy?" And the father said, "Yes, but I will need to check your letters." So in order to show, his love to her, so Descartes, he sent a letter to her with just this equation. Rho theta one equals to 1 minus sine theta. He didn't show the plot. So people who inspected the letter didn't understand it. The inspector thought it was just very regular mathematical, a letter for mathematical communication. So he passed it. And then the princess saw this equation, immediately understood the meaning, which is actually a heart curve. And then so this is actually using the mathematical way to show your love to your girlfriend or boyfriend. So that's the story. And let's see how can we use Python to do it. And you know what? Later you can, for example, send the person just a Jupyter a Jupyter notebook file .ipynb, and you can just write this code, and then let him or her run the code, and then him or her will see what it is. Okay, so we will need to run this polar coordinate, and hence we'll write it this way. We'll have theta equals to, first of all, we need to generate a linear space, but be careful since theta is the polar coordinate. It won't be from 0 to something. Instead, it won't be something like that, negative 10 to positive 10. Instead, it will be from 0 to 2 pi, okay? So we'll have theta equal to np dot linear space, and from 0 to times np dot pi. And let's say we need to generate 100 such number, and then we can print theta actually. And you will see there are these numbers. Okay, and then I will have PLT. I want to set up the axis of PLT, and here I will have the polar equal to true. So this is to show the coordinate is gonna be polar instead of our traditional coordinate, XY coordinate. And then PLT dot plot, similar things. We have what? We have theta, right? And then the other one is 1 minus sine theta. So I will have 1 minus np dot sine theta. And finally, I can let let's say color equal to R. Then here, again, I forgot. plt.show. Here we go. Or you can say color equal to I, it doesn't matter. It just shows, the keywords. And indeed, this is a beautiful and romantic heart curve, which was, the love letter Descartes sent to the Sweden princess. Uh, uh, Later, people actually redesigned the equations of the heart, and it's shown here. And we have so many hard equations. And here I actually showed another hard, which one? I believe this one. Yeah, x equal to 16 sine cubic t and y equal to 13 cosine t minus 5 sine cosine 2t minus 2, whatever. It's too long, hate to read so long things. And the things that's very long, so I'm not gonna plot it in the class here, but if you want, you can just, type it by yourself in Jupyter Notebook. It's a super, in my personal view, it's a super beautiful, perfect like heart shape. And then, this is the result. And the third thing is a 2D scatter plot. And the people may ask, since we've already used plt.plot, why do we need to learn the scatter plot? Because scatter, if you can use scatter plot, it can, you can have more controls for the plot. Let's see the example here. So here we have the line space here, scatter. Okay, so here I have x equal to mp dot linear space -1, wait, -10. Let me see here. 10, and I can close this actually. Don't save. 101. Okay, now I can have y equal to mp dot sine x. So I have x as mp sine x plt dot scatter x, y, and then here I need a keyword marker. Let me see if does it. Okay, good. I press shift in the table here, and it shows me the documentation here. Scatter x, y, and the asset size C is color. Marker C, a map is the color map, but let's say here marker equals to O. O means it will be those kind of solid points, and the color equal to blue. And then I'll have label equal to, let's say, sign function, plt dot show. There we go. Okay, I forgot the legend again. Sorry. plt dot legend. Here we go. So this is a sign, beautiful sign function here. And indeed, you can see scatter. I can control marker, color, label. And then I believe in the next example, I can show you something more magic, which is show a color map control. So here I will need to import, let me just put it here. I will need to import a random library, random package, I shall say, it's actually a Python self-built library. So random, it shows many those kind of random number generation functions. Later we'll use these. Let me first use x. I'll create x, y as empty list. And also I will need to create two more lists, colors, and also sizes, which will be used to save colors, each colors for each XY data and the size for each XY data, and then they will be randomly generated by this random package. Okay, for I in range here, I have 100. So it will actually generate 101 instead of 100. Oh, sorry, it will generate 100 from 0 to 99 instead of 1 to 100. X dot append, let's say random dot rand int, rand int. Rand int means I'm gonna generate integers, okay? Generate an integer between 1 and 100. And then y dot append rand, I believe random, sorry. Random dot rand int 1 to 100 as well. So these two lines, by these two lines, I'm generating the x and y coordinate for each point. And then I'm gonna say colors dot append random.ren. Be careful that color, it is, we generate, it is a number between 0 to sorry. I believe here, random.rand is to generate a number between 0 and 1. And I can use this one to show, to use it in colors. And finally, sizes dot append random dot, here, sizes is again a rand int to generate an integer between 1 and 500. And here now I can use a plot I can use plt dot scatter to plot this x and y, and c is the colors, and then s is the sizes, and then I will have what, again, I can have a look here. Okay, and then I can have the alpha equal to, here in the slide I use 0.3. This is actually the transparency level, and I can write plt dot color bar. This is to tell Python, hey, I want to show the color bar on the right side of the plot, and now plt dot show. Here we go. Okay. What? Oh, plt not plot. Sorry, plt dot show. Okay, here we go. And it's a pretty beautiful, and you can see for each point. So here I generated 100 points. For each point, its x, y coordinate is randomly selected. Their coordinate must be between 1 and 100. The color is a number between 0 and 1, and you can see here's a color map. And then I can accept c equal to color. This c means the color. Okay, c means the color. And the size is generated automatically as well, randomly as well. It's a random number between 1 and 500. I can make it 100 as well. Let's see. It will be very small because it's much smaller. This alpha is transparency level. So if I write alpha equal to 0, that means it's completely non-transparent. Whoa, 1 minute. Let me see here. Completely transparent. Sorry. It's completely transparent. And if I write alpha equal to 1, that means it's completely non-transparent. So you can just play the game by yourself. You can set up whatever transparency level it is. And indeed, you can see I do have more controls by this scatter compared with plot method. So this is to show the difference between scatter and plot. Later in further those plots in other lectures, you will see more applications of plot versus scatter. Okay, so the next one will be let me see. Okay, it's already 7:08. I mean, in in CST. So I'm gonna stop the lecture here. Before the next class, remember to re-download this one remember to re-download this lecture, because I will definitely add more slides to include the 3D plots. Okay, so this is everything about today's lecture. Thank you very much and have a good night. Bye-bye.